Okay, so uh, you have a sequence of random variables. Mm, Here, the sequence index is sort of time, you can say. Um, so each time you accumulate the random variable twice, that is xn. So at any point of time, you have accumulation of all the past random variables. So yeah, y1 to all whatever you observe y's, right? All y's are IDs and zero mean and with the variance of 4. So you want to find the autocorrelation of uh, random variable x, right? So autocorrelation is simply uh, expectation of the random variable sampled at different times, right? So that is x of m and x of n. So simply just take the product of these two x of m and x of n, right? So what do you get? Because it is the sum of sum over first and random variables, you have to take the product of the entire sum. I mean, indices you have to cannot use the same index, right? Uh, so this is nothing but ij running from 0 and m and n respectively. So yi, you can push this e inside sum due to the linearity of expectation, and because of IID and zero mean, right? All the terms that are which differ, right? I is not equal to j, they all get uh, cancelled. I mean zero. So what are remaining is the minimum of m comma n, right? Whichever is minimum, that much sum you have. So that's it. So it's because of zero mean, second moment is nothing but the variance. So that is 4 times min of m. So we can try doing the cross correlation between x and y. What would be the cross correlation between x and y? That is simple, but you can do that. So answer is 4, but under a condition it will be 4. Otherwise it will be 0. You can try that. Yeah. So just uh, yeah, the quick uh, thing on Poisson process, because the second question is to find the autocorrelation of the Poisson process. I mean, I think if there is separate topic on this, we will discuss in detail going forward. But yeah, just so Poisson process is nothing but a counting process. Okay, with the rate. What is a counting process is you keep counting the events. So n of t takes a discrete value, and whenever and positive values, right? So if t1 is greater than t2, then n of t1 will be greater than or equal to n of t2. It is non-decreasing, right? That's a counting process. That's it. So first of all, it has to be a counting process, and when you start at time t is equal to 0, it is 0, and it should have stationary and independent increments, right? And then at any time instant t, the probability of n of t is equal to n should be Poisson with parameter lambda times t. So that's why lambda is a rate here. So if your arrival rate is say 5 events per second, so in let's say in time t in 10 seconds, So you have 50 events. That's why lambda is typically referred to as rate in this kind of scenario. Right. So I said stationary and independent increments. Right. So what do they mean? Right. First is the independent increments. If for all times T1 is less than T2 is less than T3 less than T4. Right. So the number of increments uh, between T2 and T1 should be independent of increments from T3 and T4. So any disjoint intervals, your increment should be independent. And even more specific, right? For all s greater than t positive, right? N of s minus n of t. That means between s and t, your increment should be independent from between t and j. So in this case, it is n of t because n of 0 is 0. Right now, next thing is stationary increment. What does the stationary increment says? So n of t2 minus n of t1. I mean, it's a random variable, right? Because n of t is random variable, and it should have same distribution if you time shift it, right? So if you evaluate n of t2 by shifting by some tau amount, right? Even then, it should have the same distribution. So that's a stationary increment, right? So if it satisfies, if a counting process satisfies these conditions, then it is called as Poisson process. Yes. Okay. So find the mean of the Poisson process, right? What is the mean? Mean is the just the expectation of n of t at any time t, and because it follows Poisson distribution, you know the mean of Poisson distribution is the parameter itself. Here the parameter is lambda times t, so that's why it is lambda t. Uh, um, okay, so we want to find the autocorrelation of the process. Now, this is by definition the first line, and in the second line, you just add and subtract n of t1 to n of t2. Okay, so you just expand this and you get this thing, right? Now, uh, if you notice, the expectation is split into, uh, it is taken over product. Why? Because of independent increments property, right? Only then you can take this. Right now, the second step is P of this is straightforward, but this to this, can you guess what property we have used? I've written there, but um, this is because of stationary increments, right? So if I subtract a constant amount from this things, right, then it should have same distribution, same means same expectation. So I subtract t1 from this thing, right? So it will become n of t2 minus t1 and n of t1 minus t1. Because n of 0 is supposed to be 0 for Poisson. So that's why we get this. And so that's it, right? So it's straightforward. Again, this is lambda times t1 times lambda times t2 minus t1. And this is second moment. That is nothing but the mean plus variance. So you have this. Finally, you have this thing. But because you don't know which, we assumed here, I think t2 greater than t1. We don't know in general which one is greater. So we take the mean of t1 and t2. So any questions on this? because we don't know which of them is minimum, right? Here we assume T2 is greater than T1. So all of your things are valid if T2 is greater than T1, right? This is defined only when T2 is greater than T1. What if T1 was greater than T2? So in your final expression, this is symmetric, right? In T1 and T2. And here, because you assume T1 is greater than T2, sorry, T2 is greater than T1, you have lambda T1. Else you would have had lambda T2. That's why it is min of T1, T2. Okay. So, mm, right. So now consider a Markov chain with three states, one, two, three. And we have transition matrix like this. So this is 1 by 2, 1 by 4, 1 by 4, 1 by 3, 0, 2 by 3, 1 by 2, 1 by 2, 1, 0. Right. So you are given initial distribution uh, x1 is 1 and x1 taking state 2 is 1 by 4. What is x1 taking state 3? Uh, any guess? You are given with this 2. What is the probability x1 taking state 3? You have only three states, by the way. Mm, no, it is you have only three states. You know the probability that for two states it is 1/4. What would be the probability for third state? Yeah, so total should be one, right? It can be in any one of those states, right? So because the sum has to be one, the probability that you will be in third state is half because each of them is 1/4. Okay, so now you want the joint probability that x1 is 3 and x2 is 2 and x3 is 1. By the way, this x index is the time index. Okay, and this 3 to 1 is the state index. And these are the state indices, whatever I'm highlighting, right? And these are the time indices. This suffixes are time indices. So by first principles, you just expand this. Probability x1 is equal to 3. Then probability x2 is equal to 2 given x1 is equal to 3. And probability x3 is equal to 1 given it should be actually x1 is equal to 3 and x2 is equal to 2, but because of the Markov property you only condition on the recent past, right? So that is x2 is equal to 2. And what is this you know because of this thing, right? 1 by 2 you just computed it. And what would be this? So this is your transitioning from state 3 to state 2. So state 3 is this and 3 comma 1 is this, 3 comma 2 is this. That's why it is half. And the final one is transition from state 2 to state 1, right? So this is state 2 and state 1, 2 comma 1 is this, right? So this is 1 by 3. That's how it is 1 by 12. It's clear, I guess. Okay. And then I'm sorry for this thing. Uh, so we are given a Markov chain, um, right? And with three states, and the transition matrix is like this: so 1/4, 1/2, 1/4, and 1/3 is 0, 2/3, and 1/2, 0, 1/2. And your given initial state is 1. Okay, you start with the state 1. And R is the first time that uh, your Markov chain returns to state 1. Okay. Um, so you want to find the expected time of this uh, random variable R, right? So I think in it the identity we use here is the expected return for a state to come back is nothing but your 1 over the probability of the stationary distribution, right? So we just find the stationary distribution by using the pi is equal to pi p, right? So Markov chain has to satisfy this if it has the stationary distribution, right? So yeah, we just do this, right? So this is not y, this is pi 2, right? I made a typo there. This is pi 2. And you just expand this equations. You get three set of equations along with this thing. Pi 1 plus pi 2 plus pi 3 is equal to 1. Right? When you solve it, you get pi 1 as 6 by 16, pi 2 as 3 by 16, and pi 3 as 7 by 16. Right? So your desired answer is 1 over pi 1. Clear? Yeah, you should look up to the derivation of this identity. And yeah, so so you want to determine, given a Markov chain with a transition probability matrix as this thing, if it is aperiodic and irreducible. Uh, I think I have written somewhere. Okay, let's do this first. Uh, Here, right? Markov chain is irreducible if all the states are reachable from every other state. Okay, and it is aperiodic if the period is 1. I think period also I think I'll define somewhere. Okay, so basically it is aperiodic if the period is 1. And so you're familiar what is the notion of periodic in this context? So periodic means so period. So, mm, so period for a uh, state is the the greatest common divisor of a set, and for which you have it where it has a positive probability of returning to that state. Okay. Uh, so I think I'll try to get all these definitions in one place, maybe in next session. So take it for granted, okay? For now. Um, okay. So and for this thing, you need to find this thing whether it is irreducible, and it is aperiodic, and whether it has stationary distribution or not. So it is irreducible. It is easy to see because all the states can be reached from every other state. From state one, you can go to two, and you can go to three. From state two, also you can go to three directly, and you can directly go to one. Okay, and of course you can come back to two also because you can go to one and then come back to two. And from state three, also you can go to two, and you can go to one, and you can of course come back to three. Okay, so it is irreducible. You can reach every other state. And a periodic. Um, so whenever you see a self loop, right, it has a period one. Okay, and when you find a chain is irreducible, then all the states will have same period. This is also a result. Okay, so these are useful in identifying whether a chain is irreducible. And because you know one state it has a period one, and you know that it is irreducible, then all the states have same period, and that's why it has a period. Markov chain has a is a periodic because it has a period one. Okay, so you just have to stationary distribution. Everything straightforward. You just have to write down those three equations and the constraint um, that that all the probabilities should sum to one. Basically, this thing. Okay, and yeah. So this is another question where you have to determine if the Markov chain is periodic and irreducible. So you can see that you can reach to every other state from any state, right? That guarantees the irreducibility. And once you see a loop, it is one because it is irreducible, and one state has a period. One state and all the states should have same period, and you know that one state has one. So all the states should have the same period. Okay, so it is both a periodic and a reducible. And I think this is the last question for the day. Here you have so another notion is do you know what is positive recurrent, null recurrent? The period of the state is the um, just try to write down. It's the GCD of n such that p of x x is positive. Okay, so that's how you find the period of a state. So that's why whenever you have n as any self loop, right? So you have one in that set. Once you have one, then the GCD will be one, right? The greatest common divisor. Once you have one in that set, the GCD will be one. I'll try to put all these definitions in the next uh, session. Okay. Uh, yeah, so this is again a Markov chain. Now we want to find which states are positive recurrent. Uh, so, uh, so you're familiar with transient states and recurrent states. Transient states and recurrent states. Are you familiar with them? Okay. Okay. So what we can do is probably we can skip this slide. Um, so in the next week, I'll try to list down all this definitions and any important results. Right? So that would be helpful. So maybe you should also go through these definitions and all ones. Okay, so yeah, so maybe next week we can solve questions. So where till which point the lectures have been covered? Let me stop recording.